Okay, I think we can start. It's a real pleasure for today's Séminaire Général to have Per Berglund from University of New Hampshire, and he's going to tell us about Calabi-Yau manifolds and machine learning. Please.
Thank you. It's a great pleasure to be back at Saclay. I was here, I think, last time in 2017. Great to see familiar faces and new faces as well. So I'm going to tell you about some work that I've been doing over the last 3-4 years, where I've taken to at least work with people who are very proficient in machine learning and apply machine learning to Calabi-Yau manifolds. And the general context is, string compactifications and Calabi-Yau manifolds. In fact, I was overhearing some conversations among students and junior people here, about string compactifications, Calabi-Yau manifolds. Of course, it's important in trying to reconstruct or understand the four-dimensional physics that we observe, and some of the latter part of the talk will be focused on, in principle, being able to calculate Yukawa couplings in an effective theory in 4 dimensions. Although we're not claiming that this particular calculation is directly relevant for anything that you can observe, let's say at CERN. But in principle, it's a point of principle calculation using machine learning to solve for the Ricci flat metric. So I've been working with a number of excellent people, including students. Ben Campbell was an undergraduate student with me. Of course, Vishnu Jejjala has been working in the field for a long time. And then as Yang He and the students at the time, Ellie Hayes and Ed Hirst. And then, of course, Lukas has been in this field for almost as long as I have. Of course, my old friend and collaborator, Tristan Hübsch, and then some more junior people, including students, Justin Tang, and my own student, Butbaia, who was just an amazing asset. Much of this part of this presentation is due to work, the presentations he's given, and in particular, this rendition here of the Calabi-Yau manifolds, which I'll come to a little bit later, is his work. And of course, Challenger Mishra and Peña, more junior scientists. And I should say that much of what I'm going to be presenting here is due to their insights, but the presentation or the what I'm saying here is any mistakes are mine. Okay, so without further ado, let's get started. So here is a brief overview of the presentation. Oops. So I'll start with just very basic introduction, the role of machine learning in string compactifications. I'll then come to the first topic, which is computing the Hodge numbers, in particular the difference of the Hodge numbers, H11 and H21, which are the two non-trivial Hodge numbers in a Calabi-Yau manifold. That gives you the difference gives you twice the difference gives you the Euler number. So the difference between the Hodge numbers is related to in a simplest heterotic string compactification to the number of generations, and how we can use machine learning in a particular database known as the Kreutzer-Skarke database. I'll then move on to a slightly different aspect of machine learning using genetic algorithms to construct new Calabi-Yau manifolds by constructing reflexive polytopes, which is essentially the type of work that Kreutzer and Skarke did in the 90s, from which one then can find these so-called toric varieties in which a Calabi-Yau manifold is embedded as a hypersurface, and how we can use genetic algorithm to construct new higher dimensional polytopes relevant in principle for F-theory compactifications, a generalization of type 2b string theory compactifications to 4 dimensions. And then the second half of the talk is then focused on Yukawa couplings and the calculation in particular of Ricci flat metrics, which has been a field that's gotten a lot of attention in the last 5+ years, and how we and others as well, use the metric on the Calabi-Yau to then normalize the Yukawa couplings in heterotic string compactification. And then I'll just finish with some concluding remarks. So let's just briefly start with some words about where machine learning fits in string compactifications. So as I was saying, if you take the heterotic E8 cross E8 theory, one of the string theories, and then you compactify on a Calabi-Yau threefold, then in the simplest form, in the so-called standard embedding, the number of generations is related to this topologically invariant, the Euler number, which is twice the difference between the two non-trivial Hodge numbers, the number of non-trivial 1-1 forms and 2-1 forms. And it turns out that in this data set that I will be presenting shortly, one actually can find a very simple formula that tells you what the Euler number is, an exact formula that we sort of indirectly found through machine learning. In fact, machine learning 101 in the end, which is just linear regression, but we didn't realize that in the very beginning. In terms of this underlying data of these special polytopes from which the ambient space is constructed. So then the other part, which I've just already discussed, is how we can generalize this data set of Kreutzer-Skarke using genetic algorithms. And then the final thing, these normalized Yukawa couplings using a special form of what we call spectral neural networks, in which we can define a global function phi that is part of how we solve for the Ricci flat metric, from which you then compute the Ricci flat metric. And in fact, it's that function phi that is rendered on these on that picture of the Calabi-Yau. Okay, so moving on. Back in the 90s, originally by the work of Batrev, it was realized that so-called toric varieties, which had been studied, since the 70s, these are essentially generalizations of complex projective spaces. Batrev realized that you could understand mirror symmetry, which is this idea, which I'm not going to be spending too much time on, but it's the idea that if you have one Calabi-Yau manifold, there exists another Calabi-Yau manifold where the role of the Kähler deformations, changing the size of the manifold and the is exchanged with the complex structure deformations, and there exists this other manifold where those roles have been interchanged, and the calculations can be done very easily in one versus another. And this was done in the context of these toric varieties, and the toric varieties are constructed by starting with so-called reflexive polytopes, which I'm going to describe in a little bit more detail in a second. Kreutzer-Skarke then, this classification of the reflexive polytopes, the two-dimensional reflexive polytopes, they were known for since ancient times. The three-dimensional and four-dimensional ones, that classification didn't exist, but Kreutzer-Skarke through very ingenious computer work, we're able to compile a list of all of these polytopes. So in 4 dimensions, there exists this number of about 500 million of these reflexive polytopes, from which one then can construct 4-dimensional, complex dimensional ambient spaces in which we can then embed a Calabi-Yau hypersurface. So now, what's the role of the machine learning, or the neural network? Well, it turns out that if you are looking at, and this is just a simple toy example here of a two-dimensional polytope. So this particular polytope here, that is the smaller one that's inscribed here, delta star, is the polytope from which one can construct the complex projective space of dimension 2. And so it's this space in which we would then have a hypersurface, which in this case would be a Calabi-Yau one-dimensional hypersurface, and the only Calabi-Yau one dimension is the torus, and the Calabi-Yau condition is given by providing a cubic defining equation. And on this side here, the original so-called Newton polytope delta, each point in this inner triangle here corresponds to a monomial in a cubic monomial, and if you count these, there are 10 monomials, and those are indeed all the possible terms that you can write down in defining equation. So now, and these two polytopes here are dual to each other, and the property that says that they are reflexive is that they are integer lattice polytopes with one interior point, and the dual polytope is also an integer lattice polytope with one interior point. If we wanted to construct the mirror of this, then we would think of this polytope here as defining a ambient space. In fact, an ambient space which is an orbifold of the complex projective space of dimension 2, in which we then could embed a hypersurface. Oops, no, I did this. I made a mistake here. Clicking. Oops. Okay, now we're working it. Okay. So this is how mirror symmetry would work. You would define then a hypersurface of also degree 3, and in this case there are 4 invariant monomials associated to the 4 integer lattice points in this interior. Okay. So now, what is the result? Just to give you the result, it turns out that the calculation for these 4-dimensional reflexive polytopes that tells you what the Euler number is given by specifying just these 4 integer numbers for a given polytope and its dual. So here, what do I mean by 2 delta? 2 delta is the scaling up the original polytope delta by a factor of 2, and 2 delta star is the scaling up the delta star, the dual polytope, also by a factor of 2. So if we're counting an L of delta is the number of points, so L of delta here would be 10, L of delta star would be 4, and then you could calculate what the number of points is if you scale it up. And now in this case it's not relevant because this is too trivial of an example, but if you were to do this now for one of the 4-dimensional reflexive polytopes, we'll show later on in a minute that there exists an expression for the Euler number, the topological invariant, in terms of just these 4 numbers here, which is quite amazing given that there are lots of different ways in which we can construct these reflexive polytopes, invariant ways, for 500 million of which. And the Euler number for the Calabi-Yau is just given in terms of a simple formula, just given by these numbers here. Okay. Yes.
So I'm out of this field. I really don't understand what type of problems. What physics problems are you trying to solve? And which type of? To me, I don't understand anything.
Okay. So the physics problems here is if we go back to the motivation is to take string theory, heterotic E8 cross E8 string theory, compactify it on a Calabi-Yau threefold, and then construct the 4-dimensional effective theory. And in the simplest construction, that 4-dimensional effective theory has the number of generations in that theory is related to this topological invariant, the Euler number. And we have, if we take a particular class of models, which are these hypersurfaces in the toric varieties, which are constructed from the polytopes.
Maybe that's what he didn't understand. So the
Yeah.
first part was clear, but
Yeah.
what's the dimension of the polytope, what's the dimension of the hypersurface, what's the equation construction? I mean, no.
Yeah.
I think this kind of thing is missing. So maybe
That's
you
right,
have it
that's
on the
right.
next slide.
Yeah. So we're going. Okay. So we're going to. Let me go to another slide here. Okay. So the physically relevant case is this one here, where we're in 4 dimensions, and the 4-dimensional reflexive polytopes are related to 4-dimensional ambient spaces, of which the simplest one would be a complex projective space of dimension 4. In that space, we embed a hypersurface.
It's an 8-dimensional space, right?
It's an 8-dimensional space. The hypersurface is a complex polynomial defining equation. So that reduces the resulting Calabi-Yau manifold to be a 6 real dimensional manifold or 6 complex dimensional manifold.
But I'm sorry, you are trying to solve any field equation for a metric or whatever. Where does this reflexive polytopes come out? I don't understand.
Okay, so it's not obvious from the beginning where this, but there's a relation between the combinatorial information of a polytope and the complex geometry of, or actually a Kähler manifold. So it's a complex manifold of special kind of Kähler manifold in which we can define a hypersurface that is the extra dimensions of string theory that string theory predicts. And obviously those extra dimensions are very small, and we would, by compactify the 10-dimensional string theory, so by assuming that the 10-dimensional string theory lives in a flat Minkowski space, and the resulting theory that you get, the effective theory, once you write down an action, a supergravity action in 10 dimensions, you compactify on that 6-dimensional manifold, you get a 4-dimensional effective theory that would include gravity, but also would have a particle spectrum, depending on additional information. But in particular, the relation between the geometry, the physics of, the mathematics of the geometry, the topology of the geometry that we're talking about here, gives you the information about the number of generations. And so we have this laboratory of many different ways in which we can compactify on these Calabi-Yau manifolds. And what we're interested in this particular setting here is to understand how, in this landscape of these different choices, how a simple quantity such as the number of generations is related to the properties of these reflexive polytopes. Okay? So that is the mathematics of the combinatorics of the polytopes give you information about the particle physics. That's essentially the one line. And there is a way in which you could define, given one of these polytopes, as I was saying, you can define the ambient space in terms of by providing the mathematical construction of the so-called. Okay, so right, so once again, given the combinatorial information about these polytopes, we can construct something that generalizes a projective space, a complex projective space. And from that projective space, we define a Calabi-Yau by providing a particular type of a polynomial defining equation. And Batrev provided this, and then Batrev and Borisov in the 90s, a prescription of how, given a polytope delta, we construct a dual polytope delta star, and this provides you then with a way of constructing this extra-dimensional space, the Calabi-Yau manifold. Okay, now the point of this exercise is that what we want to do is we want to take a sample of this large, we're not using the whole $500 million data set of these polytopes, but we are taking a small sample of them, and about, I think it was 1 million, so I didn't actually provide this here. We train on 800,000 of those polytopes. We have a structure of these 5 inner layers, 300 neurons per layer, and so on. And actually, sorry, here's the information. So it's we take that $1 million polytopes, we take 100,000 of them randomly selected, and then we from that data set, we have two types of data sets depending on where we choose them from in the, I'm going to define what boundary means here. And then the input data is this information that I mentioned earlier. So if you have a polytope, you count the number of points in the polytope, you construct a dual polytope, count the number of points there, and you do the same thing for the scaled up and of these two polytopes. So these are the four numbers. And from these four numbers then, it turns out that the neural network will provide a relation such that we can compute the Euler number. So what we do is we know all this information. So you might think that this is an exercise that, what's the point of this? Well, we want to just see to what extent you can learn some new information by, in a different way, by calculating this invariant, this topological invariant, the Hodge number, the Euler number. Yes.
Sorry, why is L delta star an input? When you are given L delta, don't you have the mirror dual?
If I'm given L delta, so the input, given a polytope, let me just go back here. You do. So if you from delta, you can immediately calculate what delta star is.
Oh, so if you know L delta, you know L delta.
Yes.
So it's not free.
No. So these are. I'm not learning L delta star. What I'm doing is I want to learn I want to train on the known Euler number for a set of polytopes, and then so that was here. So I do a split. I take this set of polytopes, I train on them, 80,000 of these polytopes. I train on them, knowing what the Euler number is, and then I take 20,000 of them and I test to see how well I was able to train. Okay, to predict the Euler number based on what the neural network learned. Okay, so in all of these cases, and then I compare to see how well it does. Yes.
Question.
Yeah.
Do you give an Thank you. Are you giving an ansatz for the form of the function?
No. So a priori, you might have said, okay, what should these numbers have to do with the Euler number? And so all I'm just saying is that, well, what if I just had given L delta? Maybe one input. Could I have learned the Euler number from that? Okay. Or could I have learned the Euler number by providing the details of what the vertices were for the polytope? And we tried that, and that was not successful. Yes.
Yeah,
right.
I still don't understand the physics problem, but maybe I can try to understand this.
Yeah.
So, what's the input of this network? The sides, the first layer. I mean, what do you inject in that, and what's the output? What's the class of function that you consider, and why do you do that?
So the input are just these four numbers.
So it's it's a vector of dimension 4 in input.
Input, and
Okay.
the output is a number, which is the Euler number. Yeah, an
It's
integer.
an integer.
Yep. Yep.
Okay. And what do you put inside? So
This is just a regular feed-forward network.
Mhm.
Yep. Convolution neural network. So it's
Why
just
convolutional?
just because it's it's just to try a neural network to see if it's possible to predict.
But why do you impose convolution? Why do you impose this structure on the network? I mean, this works for images. Why should it work for some very nonlinear?
That's a very good question. That's a very good question. In fact, people have looked at a different class of these 6-dimensional real manifolds, the Calabi-Yau manifolds, and with different input data, and been able to calculate not just this topological number, the Euler number, but also the individual Hodge numbers. So to an accuracy using convolutional neural network, even if you might think that, what does that have to do with with the problem at hand. Indeed.
No, I understand that this is a fitting function, but I mean,
Right.
typically, I mean, it's known that the fitting function matters. So
Right.
if you use convolution, it works if you, I mean, if in the input layer you have some local structure
Yep.
you're trying to understand, and this is, for example, typical in images or
You're right.
like
Yep.
sound or things like
Yep.
that.
Yep.
But you have as an input just a 4-dimensional vector. So
Yep.
why convolution?
Part of the story was that we, just to go back to this picture here, we started with the information for a 4-dimensional generalization of this polytope here, where we had provided the details of each of the vertices. So if you specify the vertices, you specify the polytope. And it was from that point of view, we first approached this problem. Can we, by specifying polytopes, by giving their vertices, and the number of vertices, of course, will change. So, and that was the starting point. And we realized that actually that didn't, we were not able to get any interesting results. The learning rate was not very good, or the predictions, the loss function was not giving us the kind of data that output that we had predicted, that we had hoped. And so instead, given that we had started with this, it seems like it's overkill. I agree, but we just had we had the structure in place, and then when we ran this, let me get to the results here. Actually, let me just. Then it turned out that the accuracy for the so this is showing the accuracy after running, by selecting this the training and the test data randomly. Several times, I think 5 times here, a very good accuracy. It's not perfect. In fact, it's somewhat surprising that it's not perfect for the Euler number. For the individual, these topological invariants that are related to the size and the shape of the Calabi-Yau, the accuracy was not very good at all. Okay, so let me just move on and. Here are some, further, this is now for the Euler number, which is, the confusion matrices are showing that, it's very, between predicted and actual. There are the 2 sets of data that I'm not going to, go into the details because I wanted to get some of the other parts. That's very good. So we then, and the next, did what we should have tried from the very beginning. We should have tried this. I agree. I mean, you should start with the simplest machine learning, which is just linear regression. Did the same thing with the same number of. Oops. What happened? Uh-oh. Oh, there we go. Okay. So we did linear regression on the individual Hodge numbers, but the more important thing is getting to this expression here. So we did linear regression on the Euler number, and lo and behold, one finds this very simple expression, which is completely unexpected. This result that tells you the physics is related to this part here, the combinatorics is related to the right-hand side, and from the combinatorics, we can then find an expression for what the number of generations would be in a toy version of our universe coming from a string compactification on a particular string theory E8 cross E8. Yes?
So, sorry, so what you are saying is that you take this convolutional neural network, it gives something, and then you just apply a linear regression on this 4-dimensional vector, and it gives you the same result.
Yep.
Okay.
Yeah. I mean, what we should have done, but it was just that we approached the problem. We never imagined that there would exist this expression. This result was not known mathematically for these 4-dimensional refracted polytopes. So this simple expression here holds. I mean, we have, you can check it for all the 500 million polytopes, and you get this result, which is yes, Joseph.
What's confusing me is that this is data about the polytope, but then
Yeah.
on the polytope you have to define this equation to define the Calabi-Yau. Why
Exactly.
doesn't the Calabi-Yau care about this equation? Why does this Hübsch I mean, the Hübsch number normally care about the Calabi-Yau. I have a more funny equation, I get a more weird Calabi-Yau. Why would this only care about the polytope?
So very good, very good. So given, let me just go back to, given a polytope and its dual, this here defines an ambient space. In fact, in general, there are several ways in which you can define the ambient space, and then the polynomial equation, the monomials are associated to the points here. So you might then say, okay, I can choose different ways in which I construct my ambient space depending on, the complicated space here. I get a different Calabi-Yau. However, the Hübsch numbers are always going to be the same.
Mm-hmm.
The Euler number is going to be the same.
Even the Hübsch numbers are going to be the same. Okay.
Yeah, that's right.
Okay.
So you choose a different defining equation that tells you that, okay, I have a Calabi-Yau where I've changed what's known as the complex structure, but I haven't changed the Hübsch numbers.
Mm-hmm.
So, yes.
Okay. So at the end of the day, it's just the polytope which determines everything. Okay.
Yeah.
Thanks.
It doesn't determine the details of, let's say, the Yukawa couplings. Those you have to do a different type of calculation. But the Hübsch numbers themselves only, and the Euler number in particular. So that the number of generations, which is what in this particular simple class of heterotic E8 cross E8 string compactifications, that only depends on these 4 input numbers. Okay, so let me just move ahead here. Now, at the end of the day, and I'm not going to spend any time here, one can actually show, and this was not something that was known before, but one can show why this is the case by computing, by using algebraic geometry, and get interesting, essentially derive this expression for the Euler number here exactly. Okay, and so if we now were to just to show you that I'm not making this up, if we were to look at the quintic hypersurface in P4, so L delta is the number of points in the number of monomials. So it's a quintic, so that means that you're looking at degree 5 hypersurface in 4 homogeneous coordinates in this complex projective space. And you can count those number of monomials, there are 126 of them. In the dual polytope, there are only 6 points. This is essentially the generalization of the case where you had, for the 2-dimensional polytope, there were 4 points. In 4 dimensions, there are 6 points. And then it's a little bit more complicated to calculate how many points there are by scaling up the polytope. In fact, I forgot the information here about scaling up delta star, but anyway, you can calculate those numbers, and then you plug them into this expression, and indeed you get that the Euler number, as it should be, is minus 200, which is the number, is the Euler number for this simplest of all Calabi-Yau hypersurfaces. Okay, obviously this particular Calabi-Yau is not something that would give you a very relevant particle physics. It would say that the number of generations is 100, the half of the absolute value of the Euler number, but at least it shows just the principle of the idea. Okay. The next.
Sorry, just before moving to the next part, just to understand sort of the process. You told us that you first tried machine learning and the results were not great.
Yeah.
Then you simply throw that away and tried the linear regression, and that gave this very nice and simple result.
Exactly.
So in a sense, this tells us that machine learning is not the right way to approach the problem. But I was wondering, is there any way of having a hint from the machine learning results that there should have been a simple linear relation? I don't know if that makes sense as a question.
Well, the hint was that when we did this, when we first, so the original attempt was, let's just throw the data that exists with the number of the vertices tabulated, and I'm not even showing that result because the accuracy there was just, it didn't give us anything. Okay, that information, the convolutional neural network, based on what people had done before, where they had gotten excellent results using different input data. We tried that method and it didn't give us anything. And then we simply just said, let's just make the problem simpler by just specifying these 4 numbers. That was just a guess. And it turned out that with those 4 numbers, the convolutional neural network didn't give you 100%. You might have thought that it would have learned it exactly, but it didn't. But it gave us an idea that, okay, maybe there should exist an exact formula. So then we went back and did what we should have done from the very beginning, to do a linear regression. And the linear regression then gave the exact result, which we then were able to show mathematically where that came from. Okay, so just sometimes the machine learning, or in this case the linear regression, points to something that you wouldn't have otherwise guessed, or not necessarily otherwise have guessed. Okay, that's the idea. Okay, so now genetic algorithms. So the idea is that what do we want to do? What we want to do is we want to see if we can go beyond what had been done before. What had been done before was this classification of all these 4-dimensional reflexive polytopes from which we can construct 4-dimensional ambient spaces in which we would embed a 3-dimensional Calabi-Yau. Each one of those Calabi-Yaus, if you compactify it, would tell you that you have a 4-dimensional effective theory with some particle spectrum where the number of generations is related to order number. Okay, well, what you can do, and what people have done before, is to look at Calabi-Yau 4-folds. Well, so why Calabi-Yau 4-folds? That seems, now we're running out of dimensions. But there is an F-theory generalization of one of the type 2b string theories, in which part of this 4-fold is an elliptic curve or elliptic fiber over a 3-dimensional space, where the elliptic fiber doesn't really play a role from the dimension point of view. And then you can still, because it's just the 3 complex dimensional space that matters, and that's why these manifolds are still relevant for constructing 4-dimensional physics. So what do you want to do? The exercise is now, can we classify or can we construct 5-dimensional reflexive polytopes that then could give rise to 4-dimensional Calabi-Yau manifolds, and in particular those 4-dimensional Calabi-Yau manifolds that turn out to have what's known as an elliptic fibration. So they're an elliptic curve over a 3-dimensional base that would then be used in string compactifications. So this is another class of theories that in principle could describe the physics in the 4-dimensional physics that we observe. So what's the role of the genetic algorithm? Well, here it's just impossible to even get to close to a classification of these 5-dimensional reflexive polytopes. It's estimated that there are 10 to the 20 some polytopes, so clearly we can't do that. But instead, you want to sort of get some subset and use genetic algorithm as a way of speeding up, instead of, okay, how do I actually construct these polytopes one by one? So let me just go through this relatively quickly given the time. So you start with some population, and the population here is different types of polytopes, not reflexive. And then you rate them based on how well they are close to, quote, to what you want, that is a reflexive polytope. You then have the usual selection and crossover, construct a new set, and you also have mutations to get yet a new set, and then you keep some and you throw away some based on a loss function, and you try to sort of minimize that loss function. You keep going. Okay, so there's a certain methodology here. You encode these the vertices. So n here would be the dimension. So in this case, n would be 5. You specify how many vertices you want to have, and you have to specify what those vertices are. So you randomly just select vertices. In order to apply this, the idea of the genetic algorithm, you have to make every integer entry in the vertex in a vertex to be a positive entry, so you have to subtract a certain minimal negative number so that everything becomes positive. Then you convert each of the integers in this matrix here into a binary, and then you just essentially get a long string of binary numbers, and it's that long string of binary numbers that essentially is your input data, and then you perform this genetic algorithm evolution. So let me just give a simple example. So this is just a randomly two-dimensional polytope. As you can see here, this polytope has more than one internal point, and so it's certainly not a reflexive polytope. The vertices are listed here. So here we have vertices with negative entry -2. So we need to convert this to something where it's all non-negative. So we've chosen here this min to be -3. It could be -2 as well. So this was the original list of vertices. You just string them together. You then subtract this number here to get all non-negative. In this case, it's all, they're all positive. Turn them into binary, and then you have to make them to be of the same length. So obviously this number here, 1, is this 1. So you have to, this is the bin length. So maximum here would be, something that's 7. So 0, 0, 1, and so on. And this is your input data. And then you choose a population of, let's say, 100 of these polytopes. And then you go through the evolution of that until you've constructed a set of reflexive polytopes. So depending on, you have a search space, you have the number of states, which is a very large set of states. And what's amazing about this genetic algorithm is that it's very quickly able to, just like in nature, able to find the relevant data that relevant polytopes that we're interested in. So you of course have to specify a loss function here, and the important part is this first term in particular. IP is the internal property. There's one point in the internal manifold. So when this is satisfied, then this is equal to 1, and so you get and 0 otherwise. And then you have other conditions that you may want to impose, represented by this part of the loss function, and then you also have to specify, let's say, the number of points, the number of vertices, just to simplify the search, and this is how you set up your loss function. Okay. The other thing that you have to take into account is the fact that there are polytopes that are equivalent up to permutations. Obviously, we don't care about the order of the vertices, or if there's a GL and Z transformation that relates the vertices. So we have to take this into account and compute this, the so-called normal form. Okay, we go through these steps, and then here, just to make sure that this whole principle works, in just one run, all the 16 reflexive polytopes were constructed. And these are the reflexive polytopes here. These were the polytopes that were known. And the state space here, if you calculate it, is 10 to the 11 states, depending on the number of dimensions, maximum number of vertices, and then the bin length here being 3. But the fraction of the states that one can estimate is a tiny number. So we certainly don't have to go through all the possible polytopes in order to find the reflexive ones, which is the power of the genetic algorithm. You can do the same thing in 3 dimensions. Here you have to run it a little longer to get all of these reflexive polytopes that have been classified already. Here the fraction is even less. These are examples of reflexive polytopes. 4-dimensional reflexive polytopes, they're 500 million. There's just no way that the genetic algorithm can construct all of them. But instead, what you can do is you can construct certain subsets of them by specifying the number of vertices and, let's say, the number of points. And then you can compare that with what is known about these reflexive polytopes. And these are the known number of reflexive polytopes. And it's possible by not that many runs from the genetic algorithm that we can reproduce this. Okay, so this is all known. The important thing now is going to 5 dimensions to construct new reflexive polytopes. And of course, in this case, we don't know whether we exhausted the list or not, but these are the numbers of reflexive polytopes that we have been able to construct if you start with a small number of vertices and a small number of points. Here is just an example of what if we are interested in a particular type of polytope associated with a particular type of Calabi-Yau, then one can compute by just a known mathematical formula that existed. So all of these calculations can be done in principle. The question is now, if we've now constricted a new polytope, what are the topological numbers that are relevant for the physics that we in principle are interested in? So this is just an example to show that here is a polytope that was not known before. That's been a partial classification, but this was a polytope that wasn't known before. Okay, so this just shows that this method works. And we have some conjectures here about the very simplest type of reflexive polytopes. The simplest one being where you have a very small Hodge number, that is the number of scalar deformations. This Hodge number here is 1, so these are the simplest type. This would be the generalization of the quintic hypersurface in P4. This would be manifolds like it's a degree 6 hypersurface in complex projective space of the dimension 5. This is among one of those 15. Obviously that one was known, but there are other ones that hadn't been constructed before. And so these are some further results. Okay. Now, that was that application, a different application of machine learning to the set of string compactifications, constructing new Calabi-Yaus. And you might wonder, why do we want to construct new Calabi-Yaus when we already have lots of them? Well, we don't know which one is the right one. So that's why this is, we think this is a useful exercise. Now, to finish off, I'm going to tell you about some more recent work, ongoing work as well, with my colleagues on computing the low energy effective action and in particular here the kinetic term, the normalization, which is the metric on the Calabi-Yau manifold, and then the Yukawa couplings, the trilinear couplings that would arise in a 4-dimensional theory that you would obtain by compactifying on a particular Calabi-Yau manifold. So this is where these quantities here are going to depend on obviously the number of i's and j's here. These are the number of scalar fields. They are related to the Hodge numbers, the individual Hodge numbers, H11 and H21, depending on what type of coupling we're interested in and what kinetic terms we're interested in. The actual values here are going to vary when you change the shape and the size, when you change where you're moving in this parameter space. So this is, to an earlier question here. Yes, you can choose one Calabi-Yau and you have the same Euler number. The number of generations is not going to change, but depending on how the manifold looks, how the shape and the size of it, that's going to change these couplings here. So you have a large parameter space, and we're now interested in calculating these types of normalized couplings, the physically normalized Yukawa couplings, for which you need the metric. But the problem is that the metric is not known analytically. Even if we can construct all of these billions of Calabi-Yau manifolds, and we can understand and study their space of deformations, we have not, until fairly recently, been able to, not we, but people in general, have known what the metric is. So that's what this program is about. Okay, so these are the Yukawa couplings. We need to pick a Calabi-Yau. So we could pick a Calabi-Yau that we have looked at earlier. Let's say the quintic, and we then also have to pick what's known as a holomorphic vector bundle. This is going to tell you about the gauge the gauge theory that's going to be left of after the from the E8 cross E8 compactification. Okay, so let me try to move pretty quickly here because we don't have that much time. So it's important to compute this inner product here. This is the metric, and we are interested in computing these couplings. And we need to compute the couplings that are normalized. So it turns out that, and this is known from a long time ago, that if you look at deformations of what's known as the holomorphic 3-0 form, or in this case the anti-holomorphic 3-0 form, then you that allows you to compute an integral, which is a 6-dimensional integral or a 3-complex dimensional integral. So this is a 3-0 form. You vary the 3-0 form 3 times, and you're going to get, among other things, a 0-3 form that depends on how you varied that. You change what you mean by z and z bar, the complex structure, and that will give you this Yukawa coupling in the low energy effective theory. So let me, so these couplings, as I said, have been computed before, the unnormalized couplings, and this is where mirror symmetry, this idea that you have one manifold and you have its mirror, and you can do certain calculations easier. So these are calculations that are easy to do, but there are the mirror calculation that are complicated. But by looking at the mirror, you can do them by doing a calculation on the original manifold. We're not interested in that specifically today. If you choose now a particular type of simple choice of this vector bundle, so you choose the tangent bundle, meaning that the connection on this bundle is the SU3 breaking the E8 cross E8 to an E6 cross E8, from which you then can further break the E6 down to the standard model. You can do all of this. So once again, we can do all of this without knowing this Ritchie flat metric. So what's the point of that exercise? Well, it's just the point of this exercise is to be able to compare where we know what the result is and see how well the calculation that we're doing using machine learning, where we are using the Ritchie flat metric, even if it's not necessary, to do a calculation. So it's more complicated, but at least shows that it's a proof of principle. And then in cases where we have a more general setup, we would then have to rely on the Ritchie flat metric, because in those cases, this inner product, that the normalization has to be computed using the Ritchie flat metric. Okay, so let me just speed through this. The Kodaira-Spencer theory is essentially just saying, how can we change the complex structure? How can we deform the shape of the space? Well, you just start with some manifold, and then you look at small deformations of the original manifold, represented here by this T. The number of those deformations is this first cohomology class of the manifold and in respect to the tangent space. And this is the calculation that people had done before, in particular going back to Candelas. And numerical work had been done about 15 years ago by Keller and Lukas, which we're now generalizing to the case in which you have more than just the simplest number of deformations, instead of just having a single way in which you're deforming, where there's only one direction in which you can deform the space. Here represented by, if you choose each one of the deformations here to be the same, in the cases where this space has dimension 1, we generalize this to a more general class of Calabi-Yaus, where there are several of these complex structure deformations. So let me just go through this. So here is an example of a different type of Calabi-Yau. So what is the notation here? P5 is just saying that this is a complex projective space of dimension 5. And then I have 2 defining equations, which are given here, 2 cubic defining equations And why do I have two defining equations? Well, I'm interested in this case to construct a three-dimensional Calabi-Yau manifold. I'm starting with an ambient space. This is a projective space, so it has dimension 4. This is a complex projective space of dimension 5. There are 6 homogeneous coordinates, x0 through x5, and I have 2 defining equations, so that gets me from 5 to 3. The Calabi-Yau condition is this condition that the so-called first Chern class vanishes, which is simply does the numerical relation that the sum of these numbers here, the degrees 3 plus 3, is the same as the dimension 5 plus 1. Okay, well, that may be just numerology, but that is what the topological calculation tells you, gives you a Calabi-Yau. So what is this graph here showing? The graph here is showing what happens if I change this parameter psi. So the undeformed space is, in fact, the singular space where psi is equal to 0. That's why and then on the right-hand side here, I'm computing this normalization, that inner product, G psi bar. And then I'm looking at how that metric, which is actually blowing up here, how that's changing as a function of psi. And I can do this in 2 different ways. I can, by computing this metric using what's known as periods. This is just solving a differential equation, a 4-dimensional generalized hypergeometric equation known as the Picard-Fuchs equation in this case. And comparing that with numerically solving using this Kodara-Spencer method. And as you can see, it lines up perfectly. So this shows that this, in the simplest possible case, which people had done before, well, this method, the Kodara-Spencer method, works. Here's what the metric looks by looking at the complex space, and these graphs here are similar. And this is the example for the this is the Yukawa coupling. This is the metric. This is the Yukawa coupling. In this simple Calabi-Yau manifold. Here's a slightly more complicated space. I'm not going to go through this here, but in this case, there are normalized couplings which exist for each one of these values. It should really be a histogram here with just lines for each one of them. And this particular case is interesting because it's a quotient of this degree 5 hypersurface in the complex projective space of dimension 4. The Calabi-Yau is 3-dimensional. It has 5 different deformations. So this is showing that you have a more complicated space. Here we're looking at no deformations. None of those deformations are turned on, but there are these different sets of couplings. And when you compute those, and including the normalization, knowing the metric, then it turns out that you get exactly the same result that one can compute in a exactly solvable conformal field theory, that it turns out that this particular Calabi-Yau corresponds to, which is rare, but it's a nice comparison that can be done. Yeah.
How do you get the error bars?
So this is by it has to do with you run the experiment several times, or you run not the experiment, you run so this it's this calculation here of the numerical metric, the metric and the Yukawa coupling, using this this Kodara-Spencer theory. So you have to do a numerical integration, and because this is to show it in this particular case here. Here you have a simple 4-dimensional ordinary differential equation that you solve, that you then have to analytically continue from 1 for very large values of psi, in which there's a power series expansion. You have to analytically continue that, and that's done numerically. Of course, you can do that exactly. That's what this period is showing here. In the case of this more complicated example, this is actually not possible to do, so there's a numerical error in doing that, solving essentially that Kodaira-Spencer theory. You have to do a Pade approximation, so that's where the error bars are coming from. So, you just have limited numerical accuracy. Okay. Now the very last part has to do with this machine learning. So this was not machine learning, that was just a numerical approach. The next thing is that what we want to do is we want to compute what are known as the harmonic representatives. So those are the special elements of these cohomology classes for which you then, and let me just, here, you have to, and the machine learning problem that we're interested in is solving this partial differential equation to find the harmonic representatives that are then going to be used in the calculation of these normalized Yukawa couplings. So this is a different way of computing the same problem that we don't have to do in this particular case, but this is just to show that the machine learning approach is possible. So this is, it's a physics-informed neural network that we are setting up here with this PDE. Now the first part of that, is that we're setting up a global function because we have these homogeneous coordinates, and we in principle have charts that to cover the manifold, but instead we define a homogeneous function here. This is this so-called spectral layers. Let me just go through this quickly. And we have the hidden layers that compute this function phi, which is the function that's part of the deformation that we're then using to solve. Do I have that here? Let me see here now. Where do I have my... actually, I thought I had a slide for the... No. Okay, I must have... Sorry, I took away that phi. This phi here is the function. This is that phi here. That is a projection of... because we have at least a 3 complex dimensional space, and you have to project here down to 2 real dimensional space to get a rendition. This phi is the solution using the neural network to the Ricci flat condition by solving the Monge-Ampere equation from which we can construct the Ricci flat metric. So this phi here is a deformation to an original ansatz for what the metric is on the ambient space, such that the solution to the Monge-Ampere equation gives you the Ricci flat metric, which goes back to the original proof by Yau that there exists a Ricci flat metric in these types of manifolds with vanishing first Chern class. Let me just skip this part here as well to just get to these graphs here. So now we're back to this one example, and this is here to show that we have the original analytic period. This is just solving that ordinary differential equation of degree of order 4, Picard-Fuchs equation. It's a generalized hypergeometric function. That's the dotted lines. The special geometry, that's using the periods. Those are the blue dots here. The harmonic representatives, those are the green dots. You can see they line up very well. And then there are other non-harmonic representatives. So this is where we are not solving by using the machine learned metric. And as you can see, they're not as close to what the machine learned metric and the computing this harmonic representatives give you to the known result. This was for the metric. This is for the, okay, that's also, sorry. Yeah, that was just the same thing. Now, the final thing is this not very realistic, 3-generation Calabi-Yau manifold. I think we started a little bit late, but I'm just going to, so this is an example of where the Euler number divided by 2, so the number of generations is 3. This is one of the very first manifolds that was studied in the mid to late 80s. It has 3 defining equations, so 2 cubic equations, and then a bilinear equation in 2 projective spaces of dimension 3 in this case. So it's a P3 cross P3. So it's a 6-dimensional ambient space, but we have 3 defining equations. That gives you a 3-dimensional Calabi-Yau. We can compare with these unnormalized Yukawa couplings to what people had computed all the way back in the 80s. These are, once again, this is the numerical work. This is not using machine learning. This is just the numerical approach by analytically continue using the Paddy approximation and so on to, and that's why there's some numerical errors to that type of calculation. And then finally, here are a set of couplings that involve the particles that would exist in the standard model in principle, or some generalization of the standard model. This is what these values of the couplings, which are listed over here, look like when you did not include the normalization. And here is where what they look like when you do include the normalization. So you can see that there was essentially couplings that are very close to 0, and then you get these interesting hierarchies that develop as you're changing. So epsilon here, what was epsilon? Epsilon was the deformation. So this was one of these parameters that allowed us to deform the defining equation, the complex structure, and depending on which value of epsilon you choose, you will have some of these couplings that are larger than others, but that will change as you're changing the couplings. So these are sort of interesting hierarchies that develop that could, be used to explain the hierarchies that exist between the couplings, and then these couplings, of course, are then what used to be computing masses in the standard model. The fact that you have a hierarchy among the masses of the particle physics in the standard model. Here is just we have a package that is available, and here is running a calculation. This time I actually worked very quickly. It was speeded up 50 times, but the input here was to compute the Euler number from the machine learned metric on this space. So the Euler number is something that one, of course, can compute directly, but we can also compute it using differential geometry. And you saw, well, we have to multiply by 50 how quickly that number, and then if you can see here, it's minus 144.8. So it's an accuracy of down to under 1% in relatively short time. So you take your favorite Calabi-Yau, you go to this website here, and there's this, you can click on that and you can insert any Calabi-Yau that you're interested of this type. So I'm just going to leave up these summaries, the summary slide here, essentially saying what I already said in the very first 5 minutes. Thanks for your question and your attention.
Thanks, Per. And we have some more time for questions.
So these hierarchies that you get, in principle, you can get some hierarchies from the topological numbers, right?
Yeah.
In this particular case, one doesn't.
So
this Tian-Yau.
So the Tian-Yau. So if we're looking here, there you can see this part here was what was known before, the unnormalized couplings. And you can see there are still hierarchies here. However, these hierarchies, they don't mean much because you don't know what, whether when you normalize it, what the metric is.
But why those depend on the moduli?
Well, so so these are the right. So the couplings that we computed here are these are the complex structure couplings. Let's see what is the relevant slide here. This, right. So this coupling here is, by saying that it's quasi-topological, it means that it doesn't depend on the metric.
Okay.
Right. But it's not the intersection numbers, right?
Okay.
So this is something that we know how to compute. We don't need the metric on the space.
Okay.
Yeah.
And then, so you get a large hierarchy when you go to large values of the moduli.
That's right. That's what it looks like in this particular case here. So the hierarchy, well, here, this region here, this is where there are the dotted lines here are indicating singularities. So one has to be careful to interpret this. But once you go away from the singularities, then, well, on this side there's sort of a hierarchy that existed and doesn't change much. Over here, certain couplings were larger and then become smaller and vice versa.
And do you think this is generic? This would be generic?
It's a good question. We don't know. But it is interesting that you get, obviously in this case we have several couplings. Well, what people had, the simple calculations that people had done before only had one coupling. So then obviously if you only have one coupling, let me see here now, where is it? We didn't, right here, this was the metric. So obviously here it doesn't show anything. I thought I had the slide with the Yukawa coupling. So I think that in general you'd expect some kind of hierarchies if you have several couplings, but whether they are going to be there because of going to large complex structure or at some other point in the moduli space. I mean, for example, this here, even if this is just the one parameter case, this is the conifold. So it would be interesting to understand in realistic models like here, looking at places where you have this close to the singularity, as they say, conifolds, what happens to the couplings there? Because it's in this space, as you know, this is the complex structure space. This is where we want to stabilize the corresponding moduli, which are not, here we're talking about the physical fields, but there's an associated complex structure moduli space, and we want to fix these scalar fields, and is there then a hierarchy that's developing there next to let's say the conifold? Yeah.
Thanks.
Further question? Okay, if not, before thanking Per again, let me remind you that there are still a few places for people that want to join us for lunch at La Rotonde. And so thanks a lot for attending, and thanks again to Per.
Thank you.